Hi there. Thank you for coming to our virtual talk for our paper, Accountability in an Algorithmic Society, Relationality, Responsibility, and Robustness in Machine Learning. In 1996, Helen Nissenbaum wrote the now classic paper, Accountability in a Computerized Society. She sounded the alarm about the erosion of accountability in society due to the increasing delegation of consequential functions to computerized systems. In her analysis, she described 4 barriers to accountability that emerged from this delegation. Many hands, to refer to the problem of attributing moral responsibility for outcomes caused by multiple moral actors. Bugs, the way software developers might shrug off responsibility by suggesting software errors are unavoidable. Computer as scapegoat, the shifting of blame to computers as if they were moral actors. And ownership without liability, free pass to the software industry to deny responsibility, particularly through mechanisms like terms of service agreements. Today, 25 years later, software is ubiquitous rather than ascendant. It is timely for us to revisit Nissenbaum's 4 barriers, which we do in relation to the increasingly common deployment of data-driven AI and ML systems. Our goal is to assess whether insights from that work remain relevant today, and to consider how AI and ML systems complicate, challenge, and demand more of socio-technical, philosophical, and regulatory work. In our paper, we observe that 2 understandings of accountability presently circulate in the algorithmic accountability discourse. The first, deeply explored in Nissenbaum's 1996 paper, is drawn from moral philosophy. The second is drawn from political theory and the social sciences, and is most cleanly articulated by Mark Bovins. Moral philosophy has developed a rigorous notion of accountability around blame and blameworthiness. Without being able to establish fault and identify those who are to blame for a harm, there can be no accountability. In this frame, accountable actors must step forward to take blame when they are at fault. But as Nissenbaum pointed out in 1996, certain properties of computational systems make this difficult, if not impossible. If many hands contribute to a system, it is difficult to know which hands caused a fault. If a system contains bugs, it is difficult to establish a direct cause for those errors. And the capacity of systems to be seen as responsible may result in them being scapegoated for faults that lie with moral agents, engineers, corporate executives, and users, rather than inanimate technical systems. This approach to accountability in moral philosophy places the onus of accountability on the shoulders of those who are most responsible for a harm to acknowledge their fault and accept blame, but has little to say in circumstances in which those responsible refuse to do so. However, Gary Watson and Thomas Scanlon have pointed to relationships between and among actors as producing accountability through acting according to others' expectations and being held accountable by others. These relational approaches to accountability shade into political and social conceptions of accountability, which conceive of accountability as adhering within a relationship between an actor and a forum, in which the actor has an obligation to explain and to justify their conduct. The forum can pose questions and pass judgment, and then the actor may face consequences. This formulation raises concrete questions. However, for those wishing to locate accountability within any set of social relations, questions made more difficult to answer for socio-technical systems like those that comprise the algorithmic society in which we are all enmeshed. These questions are: who is accountable for what, to whom, and under which circumstances? Accountable actors may include those who are not directly responsible for harm, but have been designated as accountable or liable because of some formal or normative agreement. Harm exists beyond the scope of those that are legally cognizable as actionable harms, which we address may be pursued in court. These harms may require accountability as well. The members of the forum may include those who are themselves harmed or placed at risk of harm, or their designees, legal counsel, elected representatives, and advocates representing publics of which they are a part. The norms of specific relationships determine the contours of accountability, bound as they are at various moments by the norms of the courts of professional ethics, democratic deliberations, and so on. The 4 barriers to accountability introduced in Nissenbaum's 1996 paper require revisitation in an algorithmic age, and the context of an expanded palette upon which notions of accountability have been constructed. We take each barrier in turn, starting with the problem of many hands. Many hands at play in the production of a system make the attribution of blame and the maintenance of an accountability relationship challenging. Algorithmic systems add complexity due to the long, sometimes recursive machine learning pipeline that involves data producers, data curators, toolkit and benchmark makers, algorithm developers, vendors and users, and other subjects. Adding to the problem of many hands is the common use of multi-purpose toolkits that might be optimized for one purpose and perform reliably under those circumstances, but then be applied to other circumstances and perform less reliably. Clearly, the problem of many hands obscures who is responsible, but also what they are responsible for, given that their activities may be lifted from one context to another by others. The problem of many hands also presents a barrier to knowing to whom accountability ought to be rendered, as risk produced in the ML pipeline might be only somewhat resolvable to individual or group level harms. In 1996, Nissenbaum defined bug to include modeling, design, and coding errors that are said to be, quote, inevitable or endemic to code. In other words, they ultimately can't be avoided entirely. They are a barrier to accountability because they undermine our ability to reason conclusively about causality and fault, making it difficult to hold anyone responsible for them. Statistical software broadens the bug-like errors that Nissenbaum classified for rule-based programs. Misclassifications, statistical error, and non-deterministic outputs each can cause harm. And just like the more classic notion of bug, they can be presented as inevitable or unavoidable, and can impede determining who is responsible for blame and what exactly should be considered blameworthy. For example, unexpectedly bad overall model performance could be excused as a bug rather than a blameworthy error. If a model deviates from its expected behavior, leading to decreases in accuracy, developers may avoid accountability by assigning the behavior to the amorphous category of bug, rather than pinpointing whether the issue is in fact due to human negligence, poor generalization, distribution shift, or other faulty behavior. It is worth noting, however, that the category of bug has become particularly slippery in light of AI and ML. The kinds of errors we describe in the paper, like statistical error and errors due to non-determinism, can more plausibly be asserted to be inherent to statistical systems. This seems to turn the idea of bug on its head, as many experts would readily call these features of machine learning. This ambiguity between bug and feature calls another barrier to the fore, blaming the computer for wrongdoing, or as Nissenbaum calls it, scapegoating the computer. In the case of AI and ML, this would include blaming the inherent statistical nature of machine learning for harms that statistics-based errors can cause. Computers, of course, cannot be blameworthy. They aren't moral agents and thus can't bear moral blame. Nevertheless, it was common in 1996 and remains common to displace responsible people by instead blaming the machine or the algorithm. One example clarified by the advent of AI and machine learning comes from mathematical guarantees. In contrast to the example of unexpectedly bad model behavior, from when we discuss bugs, one could look at the case in which a model behaves exactly as it is expected to, with the number or frequency of errors remaining within an expected margin. It then becomes possible to treat that margin as an immutable attribute of the system rather than the result of human-made decisions. The system can then be scapegoated for any particular errors that fall within that margin. Given the many hands at play in the ML pipeline, there are a host of actors who operate without clearly defined legal liability for the effects of their actions on others. Third-party data and tool providers, manufacturers of components in which algorithmic systems are embedded, data servers, and cloud computing hosts all have ownership over algorithmic systems or their components without liability, obscuring who is accountable, as with the problem of many hands. Ownership without liability also affects the very contours of what an actor can be found legally liable for, even if this does not absolve such actors of their moral responsibilities to others. So having re-examined Nissenbaum's 4 barriers to accountability for data-driven algorithmic systems, in the final section of the paper, we consider how weakening the barriers would clear the way for more sound attribution of blame, in turn setting up a stronger societal expectation for blameworthy parties to step forward and take account. However, accountability in algorithmic societies involves more. Stepping forward is a necessary component of accountability, but it's not sufficient. To build a lasting culture of accountability, a necessary supplement involves establishing persistent institutional frameworks for identifying accountable parties, such as individuals, groups, or organizations, and for calling them to answer. Any technical interventions that the research community has already developed would need to be folded into such a framework and their use justified in these moral and relational terms. For example, technical assertions of robustness say what expectations are, but leave unanswered the question of the conditions under which deviations from expectations ought to be expected or remedied. Relational treatments of these issues require that the obligation be tuned to the various needs of all members of the forum. In the paper, we take each of the barriers in turn, suggesting how a moral relational treatment could help weaken them by providing a mechanism for answering the questions of who is accountable, for what, to whom, and under which circumstances. For the sake of time, we will gloss over the details for now, and we'll close by noting that eroding the barriers of accountability is a key societal challenge requiring multiple forms of expertise, and with respect to machine learning especially, the use of these tools needs to be justified. Just as mature political governance requires durable institutions and formal attributions of rights and duties, we have similar needs for the governance of producers, purveyors, and operators of data-driven algorithmic systems. In sum, one of the key elements of our argument is that accountability is moral and relational. It depends on social, legal, and political structures that provide legitimacy for the checks actors and forums place on each other's behavior. It depends on the way those checks are internalized as professional, personal, legal, and ethical duties that motivate actors' personal responsibility. Multi and interdisciplinary research on accountability, fairness, and transparency, given its potential to bring together an array of expertise and focused on themes of equity and justice, is uniquely positioned for the future work of developing a concrete, moral, relational accountability framework. Thank you, and we look forward to your questions in the Q&A session.